we looked at the z-test before, and now we will look at the single sample t-test. This is an extremely useful inferential statistical test, and it is used to see if our sample has been drawn from a population with a known mean. And it doesn't say anything about whether the populations, we don't need to know anything about the population standard deviation. In fact, it doesn't actually need to be a normally distributed population. It just has to have a known mean. And then we'll find the mean of our sample and compare it to that population mean and see if it seems like it's a reasonable fit. So we call the population mean mu, just like in the z-test. And sometimes I will call mu the reference value. So that's sort of the value we're comparing our sample mean to. So in Excel, we calculate the sample mean and the standard deviation, and then the standard error of the mean, and then the t-statistic and the p-value. And here's an example of a t-distribution with just 2 degrees of freedom. T-distributions are always centered at 0, and then the more degrees of freedom they have, the less they look like this one, where it's got a little bit lower in the middle and a little bit broader shoulders on the edges, and the more they end up looking like a standard normal distribution. So once you get to degrees of freedom in a t-test that are more than about 12, your t-distribution looks just about exactly like a standard normal distribution. And the reason that we use these t-distributions and not standard normal distributions is because when we are estimating the sample standard deviation, we use up some of the information in our sample, and so that makes us less confident about the mean. And that's why this value here is lower and these values out here are higher. But when we have a huge sample, it doesn't matter as much. So it ends up being pretty much the same as doing a z-test. So let's use drivers on Sheridan Road as our example. So the speed limit is 45. So let's say we want to test the hypothesis that people follow the speed limit. So this is kind of an interesting example because what we're really thinking about when we say that is the average speed of our sample 45 miles per hour or lower, right? And that would suggest that they are following the speed limit. So that's actually usually what we use as a null hypothesis, right? We have this whole range of things, and then we say if it's above that. So this example kind of flips the way we normally think about null hypotheses and research hypotheses, but the math is all the same. So bear with me on this. So basically what we're going to do is we're going to do a single sample t-test to see if the average speed of our sample of drivers is greater than 45 miles per hour. And if we find evidence for that, then we reject the idea that people are following the speed limit. So following the speed limit is like our null hypothesis in this case. So again, we will use an alpha of 0.05 because that's just the way frequentist statistics roll. Let's say this is a pilot study, we want to save some time, or maybe we're only just doing it during one stats class, and so we just sample 8 cars. So since there's 8 cars, the t-distribution has the number of degrees of freedom equals to the sample size minus 1, so we have a t-distribution with 7 degrees of freedom. And the critical value then, and this is a positive one-tailed hypothesis, right, because we are going to reject the null if the average of our sample is enough bigger than 45. So it's a positive one-tailed hypothesis, so that means our t-statistic is going to have to be 1.89 or larger for us to reject the null hypothesis. So we might measure these speeds, and the mean of those is 47.25. The standard deviation is 4.71. So we take 4.71 divided by the square root of 8. That's as close as I can get to square root sign. That's 1.67. So then this value here, 47.25, the mean, minus the 45 miles an hour from the speed limit. That's going to be like, what, 2.25, divided by 1.67, standard error, to 1.35. So we are about 1.35 standard errors above the mean. So it is faster than 45 miles an hour, but that's less than our critical value of 1.89. So the p-value for our test is 0.11. It's greater than our alpha. So we cannot reject the hypothesis that drivers obey the speed limit. It is, according to frequentist statistics, it's plausible that people who are trying to follow the speed limit might, just through a little bit of random noise, show an average speed of about 47.25. So let's change the way we're going to ask the question. So we're going to do the same scenario where we're looking at cars on Sharon Road and we're looking to see if they're speeding. But this time, instead of just speeding, we're also going to consider maybe that they're driving too slowly. So we want to see if they're clustered around 45 miles per hour or if, on average, drivers are much faster or much slower. So that makes it a two-tailed hypothesis. So again, we have a sample size, we have an alpha value of 0.05, but we're going to use a bigger sample size this time with 20 cars. We'll use 20 cars because we had a non-significant result last time, so maybe that seemed that 8 is not enough, ironically. So with a t-distribution of 19 degrees of freedom and an alpha value of 0.05 and a two-tailed test, our critical values are plus or minus 2.09. So if our t-statistic comes out less than 2.09, we can reject the hypothesis that drivers are following the speed limit and say that they seem like they're slow. If it's greater than 2.09, we can reject the null hypothesis and say that it seems like drivers are speeding. So here are our 20 new drivers. And the mean in this group is 52.5. So they're going a little faster than last time. The standard deviation of the speeds is 6.24. So we have a little bit, let's see, what was our standard deviation before? 4.71. So there's more variation in their speeds too. But the sample size is bigger. So our standard error is just about the same, actually, right? That's actually a little bit lower. So now 52.5 minus 45 is like 7.5. Divided by 1.39 gives us 5.38. So that is, in fact, more than our critical value, which was 2.09. And, in fact, it's much more. The p-value for this test is less than 0.001. We would not expect to see this result if we drew random samples from a normal distribution with a mean of 45 and a standard deviation of 6.2. We would not expect to see this mean in a sample of 20 samples, even if we did it 1,000 times. So we reject the hypothesis that drivers tend to keep near the speed limit.